All right, do a share. Okay, then we'll head out to our notes. And I want the bonding notes. Okay. Everybody see my screen okay? Whiteboard here?
Yeah.
All right, excellent, thanks. I don't know, did it snow a lot where you guys are?
Yep.
Yeah, I got a ton of snow here. As you can tell, I'm actually doing this from my house. I'm like not going to the university today, even though there was stuff there I really need to do. So that's what happens. And you might have to put up with snow blowers. I got the dueling snow blowers out here. I got two guys who are neighbors, thankful to have them. And they've got these huge industrial sized snow blowers, and one comes right up against my office and makes a racket, but hey, I'll take it. So if he comes by, we'll just have to deal with him. All right, guys, so let's pick up where we left off with the video. So what we're going to find out, or probably what we already did find out from looking at the video, is that basically any kind of calculation with moles that we can do with atoms, we can also apply to molecules. All right, so let's just talk a little bit about molecules and molecular structure. I haven't really spent much time with that. So let's use an interesting one. Let's start with TNT, which you guys all know goes bang, right? So it's an explosive. And TNT is short for trinitrotoluene. That's the name of the compound. Now I give you here sort of a molecular formula for TNT. That's what you see there that I just underlined. And what you notice is that it has carbon, it's got hydrogen, nitrogen, and oxygen in there as part of the formula. So it's a bunch of carbons, hydrogens, nitrogens, and oxygens all bonded together in some way. Okay, since it's a bunch of nonmetals, you guys know it's a covalent compound. Okay, so the atoms basically have to share electrons to form bonds. Now I'll show you sort of structurally what it looks like. I mean, this is not something you need to know, but if you wanted to just kind of see what TNT looked like as a molecule, I can draw it here for you. So basically it's a 6-member carbon ring. So I'm gonna write 6 carbons here in sort of a ring type structure. I'm gonna form some bonds between them here. Okay. And then we've got these NO2 or nitro. They look a lot like nitrites coming out of this thing. And there's 3 of them here. Okay, so I'm going to stick one up here. And there's one down here and one down here. And then there is a CH3 in there, which is up front. So I'll put that down here. We're bonded actually through the carbon. And then on those other 2 carbons there, I've got hydrogen sticking out. And then we actually make some double bonds here. Okay, so that's actually what a molecule of TNT would actually look like. Okay, if we actually drew it out in terms of a molecular structure. Now, we don't need to worry about that at this point in the course. That actually comes later when we start to show these kinds of structural formulas. What we care about here is sort of the molecular formula, which is the thing that I just underlined there. So that tells us, again, not only how many different elements we've got, carbon, hydrogen, nitrogen, and oxygen, but it also tells me per molecule how many of each I've got. Okay, so you could say if I asked you how many carbons are there as part of the structure or formula of TNT, you just count them up and you see the C out front, and then you see the C6 there, you add those together, and that tells you immediately you got 7 carbons in there as part of the molecule. Okay, I could do the same thing with the hydrogens, nitrogens, or the oxygens if I want. Okay, so let's use this as an example just to answer a few questions. Okay, the first one's really kind of easy. Question is, how many total atoms are there in one molecule of TNT? Okay, so we kind of look at this and say, all right, we can just sort of add these things up, right? And what I generally like to do is look at them in terms of portions of the molecule. So I've got a CH3 there, that's one portion of the molecule. Then you got the ring system, which is the C6H2. And then you got those 3 NO2s on there. So I can kind of add up the different parts of the molecule here. In terms of total atoms, the CH3 would comprise 4 atoms, right? 1 carbon, 3 hydrogens. The C6H2, that looks like 8. 6 carbons, 2 hydrogens. Watch out on the NO2, because you're taking that 3 times, right? So that's a total of 3 nitrogens and 6 oxygens. So that would be a total of 9 atoms in that part of the molecule. Okay, see how that 3 distributes inside the parentheses there. Okay, when I add all those up, that's going to tell me that I've got 21 atoms in there. And I could actually show that as a dimensional analysis if I want to. It's just a simple matter of counting them up. But if I wanted to show it dimensionally, I could do that. I could say that 1 molecule of TNT, we've already answered the question, to be honest with you, has 21 atoms per molecule. And that's just because we always like to have things nice and pat with these conversion factors that we can, of course, cross things out. So what we see there is that we have 21 different atoms in TNT. I say different, some of them are the same, obviously, carbons, hydrogens, oxygens, and nitrogens. Everybody okay with that? So that's pretty simple. That's just basically looking at a formula and counting them up. And I could have also asked you how many hydrogens are in there. And you would have counted up and said, oh yeah, I've got 5 hydrogens in there. I got 3 nitrogens, or whatever the case may be. All right. So that's just basically showing you how to read a formula and sort of deduce how many atoms comprise that formula, and then picking out which ones are which. Now, part B is where things start getting a little bit more interesting. This is where we can actually start looking at mole conversions like we did on Friday. Everything we applied there to atoms, we can now apply to molecules or the atoms within a given molecule. So here's an interesting question I could pose. I just made these up. How many carbon atoms are there in a 0.100 mole sample of TNT? Okay, so now we got moles thrown in here, and we want to get back to carbon atoms. So now we got a couple conversions to make. So I'm going to start with the given, which in this case is going to be the 0.1 mole of TNT. So we'll write that down just like we always do, keeping sig figs. All right. So I'm already in terms of moles of TNT, but I'm trying to get to number of things, right? But I got a way of doing that, right? I got a way of getting from moles to number of things, okay? So at this point, one thing I could do, and there's several ways I could go about this, but in this case, I'm just going to go directly to molecules of TNT, okay? So that I know for every 1 mole of TNT as the molecule, I've got Avogadro's number worth of TNT molecules, right? So I'll write that down. And again, I got molecules of TNT, okay? So again, it's what I'm measuring, molecules, and also an identity, it's TNT. All right, so that, if I went ahead and figured it out, would give me how many total molecules of TNT I've got. But I've got one more step in here, right? I want to know how many carbon atoms there are. So that's where I kind of have to go back to the formula, and I've got to see how many carbon atoms I've got per molecule of TNT. And again, you can go up to the formula and count them, right? I've got the carbon out front plus the 6 carbons from the C6H2. I don't see any others. So that's a total of 7 carbons per molecule. Does that make sense to everybody? Everybody good with that? Count up a total of 7 carbon atoms per molecule. So I'm going to throw that in here. So for every 1 molecule of TNT on the bottom, I got 7 atoms of carbon. And again, that just came from the formula of the compound. Okay, so let's make sure the units do what they're supposed to do. Moles of TNT will cancel with moles of TNT. Molecules of TNT cancel with molecules of TNT. And notice in that last conversion, identity is important. I went from atoms of carbon, or rather molecules of TNT, to atoms of carbon. All right, and that ends up giving me what I want. And let's look at this. It looks like I need my answer out to 3 sig figs, don't I? And that's going to be defined by the given here. Everything else is a conversion factor that doesn't limit us. And when I work this out, I get 4.22 times 10 to the 23rd atoms of carbon. Okay. Any question about how I did that? Everybody okay? All right. So now, let's do something a little different, just adding a little more to this.
I'm sorry, can you please go back up so I can get the answer?
I sure can.
Thank you.
Yeah, if I rush, just tell me. We got time.
All right, thank you, Professor.
You good? All right, you're very welcome. I'll try to go a little slower in my scrolling here too, if I can. All right, so the next question is, how many nitrogen atoms are in a 20-gram sample of TNT? Okay, so now I have another conversion I've got to add to this because I'm starting with a mass of TNT instead of moles of TNT. Now I'm interested in finding about nitrogen atoms instead of carbon atoms. But otherwise, it's really going to be kind of a similar thing to look at. All right, so here's the deal. I've got my 20 grams of TNT, but I got to get to moles of TNT, don't I? So what's the first sort of off to the side calculation I've got to make when I think about this? Oh yeah, I need to know the molar mass of TNT so I can get from grams of TNT to moles of TNT. Because remember, moles are that central unit. Once I'm in terms of moles, I can go to whatever species I want to get to. In this case, it'll be the nitrogen atoms, but I got to get to moles first. Okay, so before I do anything else, I'm going to get a molar mass of the TNT, and that's exactly the kind of calculation we talked about in the video. So here's how I'm just going to do it back of the envelope here. I have the various elements we find in TNT. There's a carbon there, there's hydrogens in there, nitrogens in there, and there are oxygens in there. And what I'm going to do is I'm going to start with the mass of 1 mole of the atom in each case, and then multiply by the number of atoms I got in the formula. So starting with carbon, I know the mass of 1 mole of carbon is 12.011 grams. I'm just going to leave units out of this and stick them in at the end, but we know that's grams per mole of carbon. All right, I'm going to multiply that by the 7 carbons that I know I have in the formula of TNT. I'll go ahead and stick the grams at the end here. When I do that, I get 84.077, keeping all my sig figs, grams of carbon. I'm going to do the very same thing for the hydrogen, nitrogen, and oxygen. So for every hydrogen, I know I have a molar mass of 1.008 grams per mole. For every nitrogen, periodic table tells me I'm 14.007 grams per mole of nitrogen. Oxygen is 15.999 for the periodic table I was using, grams per mole of oxygen. Now I go back and I try to find out how many I've got in my formula of each one of these elements. Going back and looking at the formula for hydrogen, I have 5. For nitrogen, I have 3 nitrogens per formula unit. For oxygen, I'm going to have 6 oxygens per formula unit. Okay, so that's just going back up and counting up the number of each one of the atoms I've got in the formula. So everybody okay with that? You see that there are 5 hydrogens, 3 nitrogens, and 6 oxygens in the formula. Do your math, work across, get 5.040. That's grams of hydrogen. For nitrogen, you got 42.021. That's grams total of nitrogen in the formula per mole. And oxygen is going to be 95.994. And then get the molar mass of the compound, we just add down, right? So basically we're accounting for all the carbons, hydrogens, nitrogens, and oxygens we got in the formula. So when I add down, I get a total of 227.132. And that's keeping all my sig figs there. And that's now grams of TNT per mole of TNT. Okay, so the number of grams of TNT I've got in a mole of TNT. So again, that's just a little more complicated calculation, but otherwise it's exactly the same as what we did in the video last night. Any questions about that part of the calculation before I move on? Everybody see how I got a molar mass there? All right, so now let's finish the problem. So I'm going to start with my given. I've got 20.00 grams of TNT. So now I can use that molar mass to get me to moles of TNT. Okay, so we always use the mole as our central unit. That's where we want to go. All right, so I know that 1 mole of TNT has a mass we just calculated of 227.132, keeping all the sig figs, grams of TNT. Yeah, we got dueling snow blowers out there. I can hear them. So now what I want to do is get from moles of TNT, just like we did in the prior problem, over to number of molecules of TNT. Oh, here he comes. He's coming right up against my room here. That's good. I can get out, but you're going to have to hear him. All right, so for every 1 mole of TNT, I'm going to have Avogadro's number worth of it. So that's 6.022 times 10 to the 23rd molecules of TNT. Okay, so that gets me to molecules TNT. But where am I trying to go? I'm trying to get to nitrogen atoms, right? How many total nitrogen atoms? So now I got to go back to my formula. And I got to say, okay, how many nitrogen atoms do I have per TNT molecule? I think it's 3, right? Okay, so I got 3 atoms of nitrogen for every 1 molecule of my TNT. All right, I think that's everything I need. Let's check our units and make sure it all works. Grams of TNT here will cancel with grams of TNT. Moles of TNT should cancel with moles of TNT. Looks like molecules of TNT will cancel with molecules of TNT, and I'm left with atoms of nitrogen. Okay, looks like everything else in there is conversion except for the molar mass calculation. We got, what, 6 sig figs in that, so we're not going to be limited there. So it looks like my final answer is going to be good to 4 sig figs. So I will work this out to be 1.59 and change. I actually didn't calculate it to the right number of sig figs. If anybody's doing this, I don't know what comes after the 9. I should have an extra sig fig there. Something times 10 to the 23rd. And that's atoms of nitrogen.
0.591.
Thank you. Appreciate that. For some reason, I thought I had 3 sig figs. I think I was stuck in that 3 sig fig rut there. But you're right, there should be 4 in there. Thank you. I appreciate that. All right. So again, just one more step we need to add on to that to get back to where we needed to go. In other words, going from grams to moles, and we've got to throw molar mass in there. All right. Any questions about that one, guys? Again, just kind of adding stuff as we go here. All right, everybody got the answer written down? I'm going to scroll up a little bit and I'll try to leave a little bit of that visible if I can, in case you're still writing. And here's one final example. This kind of goes back to the blood example that we did when we were doing dimensional analysis. And that was kind of a fun one because we actually had to keep track of all kinds of different things going on in blood and also different identities of things. So this one's kind of similar to that. So let's read it out. The hemoglobin, and by the way, the hemoglobin in blood, that's the part that carries the oxygen in your blood. So it's really important to your respiration and getting your oxygen to where it needs to go in the body, right? So hemoglobin count in blood is important. So it says the hemoglobin, I'm going to just reference that as He. It's not helium in this case, but rather hemoglobin. Or rather, the hemoglobin content in blood is about 15.3 grams of hemoglobin per 100 milliliters of blood. That looks like a concentration, doesn't it? Grams per milliliters of blood. I'm telling you how much hemoglobin is in 100 mils of blood. That's a concentration. Okay, that can be a useful conversion factor for us. The molar mass of hemoglobin is about 64,500 grams per mole of hemoglobin. Okay, so That's the mass per mole of hemoglobin. And it also tells you that for every hemoglobin, we got 4 iron atoms in there. Okay? So there's another useful conversion factor. So the question now becomes, how many iron atoms are there in a 6-liter volume of blood? Now, the 6 liter comes about because that's about the volume of blood found in the average human body. So basically, we want to find out how many iron atoms are in the 6 liters of blood you find in the human body. Okay, so our given here is going to be the 6 liters of blood. So that's where we're going to start. Looks like we're only going to be good to 1 sig fig here. I'm going to put blood here because, again, we need to have our identifier because we're talking about blood, hemoglobin, iron, all kinds of stuff going on in this problem. All right, so I'm starting out with my 6 liters of blood. Now, if you look over there, I've got a concentration. It's telling me how much hemoglobin I've got per 100 mils of blood. Okay, so I can probably use that concentration to get me back to a mass of hemoglobin in the 6-liter blood sample. But to do that, I got to get my volume units to match up. So the first thing I'm going to do is I'm going to convert my 6 liters of blood over to milliliters of blood. So now I can use the concentration to get me back to a mass of hemoglobin. Okay, so for every 1 liter of blood, I got 1,000 milliliters of blood. Okay, so notice what happens. Liters of blood cancel with liters of blood. I'm left with milliliters of blood. Now I can use that concentration to get me to the mass of hemoglobin in the 6 liters. Okay, so I'm just going to multiply by that as a conversion factor. So I know that for every 100 milliliters of blood, again, keeping track of my sig figs there, it looks like I got 3 in that case. I'm going to have about 15.3 grams of hemoglobin. I'll just represent as HE. Okay, so notice what happens here. Milliliters of blood will cancel with milliliters of blood. I'm left with the mass of hemoglobin and the volume of blood in the body. Okay, so I'm getting somewhere now. Now, ultimately, I want to get to iron atoms, right? So if I'm going to get to a number of things, I can't go there directly from mass. I got to go through the mole, right? So now this is where I might be able to use that molar mass of hemoglobin because that's a conversion that gets me between mass and moles of hemoglobin. Okay. We've used this kind of conversion lots of times before. I know that for every 1 mole of hemoglobin, I put moles in the top because that's where I'm trying to go. I have a mass of about 64,500 grams. It's a lot of hemoglobin. Okay, so now notice what happens. Grams of hemoglobin will cancel with grams of hemoglobin. I'm left with moles of hemoglobin. Oh, but now I'm trying to get to a number of things. So at this point, why don't we go ahead and use Avogadro's number to figure out how many hemoglobin molecules I've got in that 6-liter volume of blood. So I'm going to bring another conversion downstairs here. So we'll go to number of items, in this case, hemoglobin molecules. So I've got for every 1 mole of hemoglobin, so I've got Avogadro's number worth of hemoglobin molecules. We'll put that in there, 6.022 times 10 to the 23rd, and that's molecules of it. We're almost done, guys. So notice what happens. Moles will cancel with moles. I'm left with number of molecules of hemoglobin in the 6-liter volume of blood. Well, now I want to get to iron atoms, right? And I have a conversion for that. I know that for every molecule of hemoglobin, which I'll put on the bottom, I have 4 iron atoms, right? So now molecules of hemoglobin should cancel with molecules of hemoglobin. And now if I do my math, I end up getting like to the way more sig figs than I need. It's like 3.3835 times 10 to the 22nd atoms of iron. But now I know that only that first 3 there is significant because I have 1 sig fig back on my original volume of 6 liters. So another way of writing this, if I wanted to, is I could just say 3 times 10 to the 22nd atoms of iron are present in my 6 liters of blood found in the typical human body. So fortunately, we got a lot of iron in there because the iron is actually the binding site for the oxygen to be able to transport it from your lungs out to where it's needed in the blood. So fortunately, we got a whole lot of iron atoms in our blood to be able to allow us to do that. Okay, guys, any question about how we set that up? And that's a really good one because this really sort of shows how we can use the units to relate a whole bunch of things together to get where we want to go. Everybody okay with that? Any questions about it? By the way, have you guys started meeting for lab yet? Maybe this week is the first week you meet. Is that true?
Yeah, we meet
Yeah.
this Wednesday.
Yeah, I'm not sure it's this lab, but another lab you're going to do maybe a time or 2 down is Avogadro's number lab. That's probably one I'm pretty sure you guys are doing, sort of a standard bonding lab. And that one has all kinds of units conversions in it like this, where you basically have to pay really special attention to the identity of the things you're comparing. So it's really kind of a neat lab because you end up actually counting drops and being able to use a drop count to actually get to an independent measurement of Avogadro's number. It's actually really neat. But there's a lot of conversions that you have to do, and the lab's really about being able to identify different things and make conversions and then use those conversions to ultimately get to Avogadro's number. But being able to keep track of the identities of the things is really, really important in that lab. So this is kind of good practice for when that lab exercise comes up. So you'll probably see that in a week or 2. So kind of keep all this in mind as you're going through those calculations. All right, guys, let's pop back over to Chem 101 here for a little bit of practice. Going back to my in class here, and we're going to go to chapter 3. And compared to what we just did, these are going to be kind of easy. So it's molar mass and mass percent. And I think I actually have something very similar to what we just had going on here. I'm going to go ahead and start that. It's about 10 minutes, so we'll have time for questions actually after this if you guys have any. Either that or we can get out 5 minutes early. I think I inadvertently had an extra point in that homework. So you actually had the option to get 6 points today instead of 5. That's good. That benefits you guys.
Can you say that again, Professor?
About the quiz?
Yeah.
Yeah, I inadvertently think I had 3 problems. I think I gave each problem 2 points. So rather than 5 points, I would have had 6 in there. So if you got all of them done, you end up with 6 points instead of 5. So that's fine.
Hey, Professor,
Just 3 an extra point in there. That's all.
I have another question.
Sure.
So I know this is like really, really early to ask about like finals and stuff, but do you give us like a list of like what's on the final, like of certain things we need to study, or is it literally everything in the course?
Yeah, it's pretty much everything in the course. And the best way to prepare for it, honestly, is just keep working all the Chem 101 questions that I assign you throughout the chapters. And I think I got the chapter 3 one going last week. And what some people tend to do is they'll work through some of the problems as you're working through the chapter to get the amount of practice that you want to get to be able to do the quizzes well. And then they'll save some back to actually go back and do for final exam prep. The reason I say that is because I'm going to basically give you a final exam in Chem 101. So it's going to be pretty much the same kinds of problems that show up in the homework. So the best way to study is to just make sure you're working on the homework. And again, you can leave some, do some now and then leave some for later or however you want to do it. But that's probably the best way to study is, you know, going back and looking at your video notes and just making sure you're keeping up with that homework.
All right, thank you.
You're welcome. And I usually also will give you a what I call a cheat sheet. I think I did that last semester where it's got pretty much all the equations and, you know, tables and all that kind of stuff you would ever need on it. So you don't have to memorize anything.
All right, thank you.
Technology is good for you guys. See, in the old days, we used to have to memorize all that stuff. And nowadays, you know, it's just so easy to go look it up. There's very little point in memorizing. It's more about what can you do with it.
These in-class questions aren't graded, correct?
You are correct. They're just for practice.
Thank God.
Yeah, don't worry about it. Just do your best and, you know, you're not docked at all if you get them wrong or if you don't finish them. No biggie. I do suggest that folks take the time to do them because any practice is better than no practice. More practice you get, the better you're going to do. I tell you, I think my neighbor looks like he has a lot of fun with that snow blower. He likes pushing that thing around. Better him than me.
Better than shoveling, that's for sure. Gosh.
Yeah, I got to do that too. I kind of finish up with the shovel, but it takes me all of 10 minutes to do after he's gone through. But he's a retired, freshly retired guy, so he kind of likes having something to do. Hopefully this is the end of it for a little while. It's supposed to get a little warmer as we get into the week, I hope.
Can you go over question 3?
How about the mass percent of water?
Yes.
Yeah, we can do that one. That's fine. Yeah, and it looks like number 4 there is really similar to the problems we were just working on. But yeah, we can look at number 3. Why don't I just go ahead and show you a setup here on my whiteboard. All right, so I want the mass percent of water in this, and we should be able to actually name that, right? That looks like zinc 2 nitrate hexahydrate, right? And I want the mass percent water in there. I want to do it to 1 decimal place. Okay, so how would I go about doing that? What's the first thing I gotta have? Just kind of talking me through it.
Would you find out? Would you break down all the atoms, all the
Yeah,
all the elements?
Yeah, that's perfect. That's exactly what I would do. And the reason why I would do that is because I got to get a molar mass for the whole compound, right? So I would break it down, and let's just kind of break it down. I got zinc, I got nitrogen, I got oxygen, I got some hydrogen, right? Is there anything else in there I missed?
No.
No, I think I got it all. So let's just count up how many things I've got in there. How many zincs do I have in the formula?
1.
1. So 1 times the molar mass of zinc, whatever that is. Okay. How many nitrogens have I got?
Is it 2?
2. Yeah, you got it. Times whatever it is 14.008 or whatever it is. Oxygen. How many oxygens do I have? That's the hard one. There's lots of oxygens going on in there. Make sure you get them all.
Seven.
So you got an NO3 taken twice there. So you take the 2 times the 3. So inside your parentheses, that gives you 6 oxygens. See that?
Yes.
Okay, now go over to the hydrate. You got a 6 out in front, so that tells you got 6 molecules of water per formula unit of the compound. So how many more oxygens do you need to add to the 6 you already had?
You're going to add 6 more,
6
so you'll
more.
have 12 oxygens.
You got it. Perfect. So you're going to have 12 oxygens times whatever that molar mass is. How many hydrogens do we have total in there, it looks like?
8.
I'm counting twice 6 is 12. I don't see any over in the zinc nitrate, right? And then you've got
Yeah.
the 6 coming from the water, so twice 6 is 12. You see that?
Yes, I see it.
Okay, perfect. So 12 hydrogens times the molar mass of hydrogen. Now I'm not going to look those molar masses up. Okay, but basically what we'll do is we'll sum up everything we get, and that's going to give me grams of the compound. I'll just call it compound per 1 mole of the compound, right?
Yeah.
So now it's asking me for a mass percent of water in there. So I kind of need to do just the water part, right? So the water part, if I wanted to get the mass of that, comes from the, well, you got to be careful. It's not just the oxygens there. I kind of have to go off by myself and do this one. So let's just do off to the side the waters, because I've got those oxygens associated with the ionic compound too, and I don't want to count those. I just want the waters, right? So we'll do waters next. So we could do the same calculation, right? I've got some number of oxygens and some number of hydrogens in the water. So let's see, for the water, I've got 6 oxygens, don't I? Just water by itself. So 6 times whatever oxygen is. And then we had the 12 hydrogens coming from the water, right? And then I can do the very same thing there. Okay, and that's going to give me a mass of all the water that's in there. Okay, because I already accounted for the fact that I've got 6 of them, right? So I'm going to get some number of grams of water in the compound. Okay, so it's not the molar mass of water. In this case, I've accounted for all the oxygens and hydrogens that came from the water, because there's 6 of them, right? So that's why I got 6 oxygens and 12 hydrogens. So that's the mass of water in the compound. So now if I wanted to actually get the mass percent of water in the compound,
Times it by 100, right?
yeah, it's the mass percent. What I'm going to do is I'm going to take that ratio of the number of grams of H2O in the compound, which I did down below, and I'm going to divide that by the number of grams of compound I've got. And then you're right. If I want to turn that into a mass percent, I got to take that ratio and I got to multiply it by 100% to do that. Okay, so basically, it's the total mass of the water I've got in the compound divided by the total mass of the whole compound times 100%. Does that make sense?
Yes, it does. Thank you.
You're very welcome. All right, looks like the time's up. Let's see how you guys did. Everybody got the first one right. That's good. Second one, almost everybody got that one right. Third one, how'd we do? Not as many people got that one finished. That's okay. And then the last one, just looked like not that many people got to it, and that's fine too. Okay, but that last one is a whole lot like what we were just doing in class here. So you've got some mass of CO2 and you want to know how many oxygen atoms are in that sample. So it's pretty much exactly like the example problems we did with the TNT. Any other questions from you guys about these? Looks like we have 3 minutes to spare. Any other general questions, guys?
Can I see the question where we did the TNT so I can take a picture of it?
You sure can. You just have to come up with which one do you want? Or just all the way to the top?
The one that was similar to question number 4.
Oh, okay, and it was grams. Yeah, it's going to be a lot like part C here.
Okay.
And by the way, you'll have all this because I'm gonna, I've recorded it and it's all going out to my YouTube channel. So if you ever need to go back and look at all of this, it'll all be there. But yeah, you've got it. So you go through the very same procedure here, but you're just looking at oxygen and CO2 instead of nitrogen and TNT. But it's same basic setup. Any others? All right, guys, if there's no other questions, just remember for next time, you got another video and another 5 for 5 quiz coming up. We're starting into empirical formula. So it's a little bit different kind of calculation, and we'll introduce it actually in the video. So be ready for that on Wednesday, guys. And I will see you then. Everybody have a great day and go play in the snow.